Today we're going to be covering computational complexity. Now the one thing about this class is that I at some points have to go back to almost pure theory, but I try to tie it back into something that makes more sense. I'm going to try to do that here, but this is an important topic that we do need to cover just so you understand computational complexity, at least at a high level, and maybe at the end hopefully you'll be able to even pick out what range that certain problems fall into. So we are going to be talking about things that are solved in polynomial time, exponential time, and some time period, some sort of finite time. That time might be measurable by months or years, or this we just know it can be solved. But the one thing that I want to talk about a little bit is that actually most problems are uncomputable. Now our minds, this might actually seem weird, and I'm hoping it does actually, but our minds actually tend to think towards problems that we can grasp mentally, that we can solve. But if you look at the bigger picture, most problems we can't solve. And I'll explain to the best of my ability why that's the case. We're going to talk about non-deterministic polynomial time. Some hardness and completeness, we're probably going to just skim over that. I don't think that's super important, but there is some, and then there's some things that you're going to want to care about, at least so you understand when people are talking about it. Reductions. And even though this is the last one, this is the one that I really hope sticks with you the most, and I'm going to try to do a really good job of building up to that. Alright, so first off, let's talk about my beautiful drawing here. This line represents computational complexity. We have 4 dashes here, and in this first little window we have P here, polynomial time. So if a problem can be solved in this range, we call that polynomial time. Then we have exponential time, and that is this subset. Now notice, this exists in this world, right? So just remember that they're inclusive of each other, because that's going to be probably important as we go forward. Actually, I know it will. And then this is whatever time. That's some measurable amount of time, some finite amount of time. And then beyond this, you notice this line keeps going. So another way to look at that is if we were to take a circle and we were to draw let's see here, maybe 1/3 of this or something, and we were to say this was P, but this whole thing is exponential. So you can kind of see that this becomes a subset of this, and then this, is an even bigger circle around that. Hopefully that makes sense. So let's talk about a couple examples here. And one of the simplest ones that I think about, which we've talked a lot about, is detecting cycles. And if you want to detect a negative weight cycle, and you wanted to run that, take a second and think about where that would fall in this line. So where that actually falls is that's going to be falling in the polynomial time. We know that we can solve that in polynomial time. It is a solved problem, very measurable, very easy to represent. Now let's talk about a chessboard. So I'm going to erase all of this. If we were to have a chessboard with n by n cells, and if they're not the same, I apologize. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. We've got our chessboard. We know the location of all the pieces. can we solve this to a victory state? And where would that fall? So the answer is yes, that is solvable. And where that falls, and a lot of the big clue here is the n by n. This falls into exponential time, so somewhere in this line. Okay. Now, another example would be Tetris. So let's say that you have a Tetris board, and you know all the pieces in advance. So I'm talking every piece that's going to potentially be thrown at you, and you want to be able to solve it from some board state. You got to take a second and kind of think about where that would fall. And remember, the board is pretty similar to this. We know all the pieces that are coming. What we end up with is somewhere in this exponential as well too. So that can be solved in exponential time. And we're actually going to talk a little bit about that because there are some hypothetical solutions to that which lead us into this magical line, which I'm not actually talking about right now. Okay, so we're going to start talking about a concept that's actually very hard to grasp. So I'm going to do the very best I can to explain this in a way that makes sense. So we're going to talk about a problem called the halting problem. And this is a very high-level concept, but say we need an algorithm that returns yes or no on whether a program has halted or not. So if an application or a program has stopped running, it returns yes. If it hasn't, it returns no. So where does that fall in this line? Do you think that falls in polynomial time? This magical line that I've got here, which we haven't talked about yet? Exponential time? Some sort of finite time? And it actually falls in none of those. It actually is not solvable for every case. There is no algorithm that can solve this for every program. And I'm going to explain to you a little bit why. So let's think about this. And if you get into data science or you get into machine learning, this concept that I'm talking about right now will carry into that, because there is no 100% solution for every possible value. So what you end up doing is you build predictions on what it should be. And the way to do that is we map this over to a table. A very simple table. So 0 being false, 1 being true. So let's just put some numbers here, right? And then our program has a finite number of bits. Every program in the world has a finite number of bits, okay? So for the value 1, 2, 3, 4, 5, 6, 7. So you can see that if we feed in the value 2, we get 1. If we feed in the value 3, we get false. And, or yes, no. This is what your decision algorithms end up needing to return, yes or no. So our decision problem ends up being something in real numbers, right? But our program is something in integers. But the number of real numbers. So what did we say? We said our decision algorithm is in real numbers, is greater than the possible number of integers. And again, I know this is confusing, but basically what we're saying is that there is no way that we could have a program that solves it for every possibility. So there are more ways, there are more problems than solutions for these type of situations. So almost every problem that we think of that is a decision problem ends up being unsolvable, simply because the amount of inputs that can be fed in is way larger than the number of solutions that we can come up with, the number of programs that we can build to actually solve that, depending on how the problem's oriented. Typically, when you write a program or an algorithm or a solution, it solves one thing and one thing only. And in this case, if we're writing a program to solve one thing, and we have all these possible decisions that need to be fed in, we're no longer solving one thing. So you almost need to think about it in a larger term, where you want to think about it like the program needs to be built for every one of the possible solutions that come in. So the halting problem is perfect, right? Because if you're running an app on your phone and you need to detect that, or you're running an app on the computer and you need to detect that, and then look at the variation of the software that's running on any different platform, that's a good way to think about it, right? So there is no way for you to conceivably write a solution for the halting problem that works across all of them. And there's also no conceivable way for you to write the number of programs that are required for all the possible algorithms, functions, programs that people can create. It just is not possible. So hopefully that makes sense, and hopefully it puts it in a little bit of perspective. So I think I beat that into the bush a little too much now, so we're going to move on. So mathematically, when we think of a problem, we typically fall in this range. So when you first come up with a solution to something, you're more than likely going to come up with some sort of exponential solution. It's going to fall in this tree here, or this line, or sphere, or problem set area. So we're going to take this to talk a little bit about this line now, which I said before is a non-deterministic polynomial complexity, computational complexity. And it's kind of a hypothetical solution, right? So no one can actually pull this off, but the computational theory is there. And what we look at this as is NP. So there's a couple different things here that we're going to talk about. So NP gets to the answer via luck. And us as programmers, we know that programming luck it's not possible, right? It's not something that you can quantify what luck is. So let's take a look at an example of what this would look like. In an NP algorithm, you somehow magically get to the answer. Okay, so let's say we've got 3 paths and we have to guess. So we take a we luckily guess. Okay, and then we go down another one that has another 3. We luckily guess again, and then we luckily guess again, and somehow magically we get a yes in this solution. Somehow magically we get here through luck. This is not realistic, but it is a non-deterministic model. And again, we can't build this, but there is a computational, this is a theoretical computational model that we can probably glean some things from, and I'm actually going to talk about a few of those. So in this magical model, we somehow found yes. So let's say that in Tetris, for example, in Tetris, we use luck. We use some sort of lucky guessing to actually place our pieces and solve a board. We could solve at an exponential time, right, by trying all the pieces. And we know that, because we know that we solve at an exponential time. But what if we guess? We guess the piece, the position, and its rotation. Then at the end we decide, did we survive? And it's really easy to compute that. Did we survive in this polynomial time here? So we know that's in the smaller section. In the theoretical NP solution, we've somehow solved this, right? We somehow magically did this. So NP basically means that we have a decision problem with solutions that can be checked in polynomial time. So we end up with this dash here. And the one thing that I will say is, like, can we say that P is equal to NP? And the answer is, who the heck knows? And if you can prove it, if you can prove this exists, you probably will win some of the most amazing computer science awards known to mankind. Because we don't know, this is theory, and we don't know that this is a hypothetical, or we don't know that this can become a realistic solution. And we definitely don't have a way to compare polynomial time to non-polynomial time to see if they're equivalent to each other. So whenever the answer is yes, we can prove it. And we can prove it in polynomial time. Alright, so that in Tetris, for example, we imagine that someone is just incredibly lucky. And you ask them if they survive at the end, and they say yes. Then in polynomial time, we can check after playing out the magical guesses that he made. So, really cool concept, really cool theory there. But at the end of the day, most likely in your career, you will not be actually implementing anything that falls at NP boundaries with the luck mechanism. That is actually a foolproof algorithm that solves something. Very easy to build AI that just guesses and makes random moves. But that doesn't mean that it's actually going to always pick the best option. It doesn't mean that we're going to actually end up at a yes at the end of the day. And a lot of AI does stuff along the lines of some lucky-based decision making based on certain scenarios, but that is not an optimal solution in the criteria that we're talking about here. So P we can solve on a computer. NP we can solve, but only in a magical fairyland. That's the way I like to look at it. We really can't solve it because simply we can't engineer or prove luck. And I can't say that enough. Alright. The next thing I want to talk about is hardness and completeness. So, if we were to look at this now, alright, this is NP. So, NP hard would be anything like over here. So this is hard. Alright? So that means it may fall on the NP boundary, but it could also be outside of that. Now what does complete mean? That means, so like if we were to look at, so like that chess example, we know that chess is EXP, exponential time complete, because it for sure falls inside of here. We know for sure the chess example falls within this bounds. If the chess example fell outside of this bounds, it would be exponentially hard in that scenario. Okay, so that's, so basically, you know, this would be EXP hard, and so on. Just something that you're going to probably need to know from time to time in your career. Or maybe not, it depends. So this ends up NP hard, EXP hard on the right side, polynomial hard, we get complete. If we fall within the bounds, probably more towards the right end. For the chess example, for example. Alright, so all of this theory is awesome. But what does this really boil down to? And to me, it boils down to reductions. So if we have a problem, let's break it down into problems that we can solve. So I'll give you a good example, and let me make sure I word this the right way. So say we have a graph. None of the edges are weighted. None of them. We could solve that problem with a breadth first search, or if we wanted to be even better, we can convert that problem to one that we can run through another algorithm. So think about that. We may end up with a problem that with a little bit of tweaking, we turn into something that has already been solved and solved phenomenally well. Hopefully that makes sense. So the first part of reduction is conversion. You want to think about ways that you can convert a problem set that you have to something that you can apply a solution to. Maybe not a known solution, but most likely a known solution. I use this quite a bit when we're dealing with binary trees, or you look at a lot of data, and it's very easy to map something to a graph, and it's very easy to map something to a tree, or it's very easy to configure it into something that can be fed into an algorithm that will solve it. For example, a priority queue for certain things, or a binary heap. With a little bit of conversion, you can turn a problem that you have a ton of complexity around, and actually potentially even move it down in computational complexity. It's really a fascinating thing to think about. And I would say graphing problems are probably the most used that I've seen. Using those to convert them to algorithms, because graphing algorithms are so well studied, and there's so many very efficient algorithms out there. If you can get your data converted in a way that feeds into these graphing algorithms to return you the result you want, there's no reason not to do that. And I hope that one day you're like looking at a problem and you're like, oh, I can apply this solution. All I have to do is convert to make that work. And the unweighted graph to the weighted graph is like a very basic example of that. So if you were to take that up a level, you may end up with graphing algorithms out of data sets that early on in your career you never even thought should have been graphing sets, but it will make sense to you as you move forward. Alright, so another one that I think is actually a really good one is the longest path. The way that actually works is you just negate all the weights, and that's another way to convert the data for that one. So I want to end this by just saying, if you have a problem and you're not sure how to solve it, but there is something that you think you could make a slight tweak or a conversion of your data or the problem itself to something that is already solved, try it out. Like I would say, that is one of the biggest things that you're going to learn in computer science going forward, is that with a little bit of manipulation, you can use very, very powerful algorithms. Are they always the best solution? No. Will it work for everything? No. But if you think a graph can be applied, if there's some sort of correlation between two data values and another and mapping things together, see what you can draw out on a whiteboard ahead of time. Because I'm telling you, that will absolutely change the way that you think about problems. And that's why I think it's important to talk about some of this theoretical stuff. And I really am, as much as I harped on this, the NP thought process about why it's a theory and we can't prove it, it's fun to think about. And it's also fun to think about that on this line here, this is a small fraction of the overall problems in the world, the overall possible problems. But yet our mind is always focused, typically in here, sometimes in here, but most likely we're going to be in this range. So let's think about this out here. Let's build a way for us to think about decision problems like we talked about. And I would say decision problems really are the key to a lot of the machine learning mechanisms that are just going to blow up over the next few years with self-driving cars, self-driving like drones for package delivery. They're going to be absolutely massive. All right, I'll end that there. If possible, use reduction. Explore reduction as just a practical thing you do when you're doing code to see if you can make things solvable that you didn't think was solvable before. Think about where your problems actually lie on the computational complexity going forward. You don't really need to become an expert at hardness and completeness, but it is just important to kind of understand the concept of that and know that NP is a magical fairyland where we can make lucky guesses to somehow get to a solution. Alright guys, I hope you have an awesome day. Till next time, take care.